Hello and welcome back to AP Physics 2, where we're going to be learning about pressure in, specifically water in this case, a swimming pool. We got example B. A swimming pool is a rectangular prism, so it's a normal rectangular swimming pool with a width of 8, a length of 14, and an average depth of 1.5 meters because it's really difficult to be apparently precise when making swimming pools. Okay, so our first question that we have with this is calculate the weight of the water in the swimming pool. And in order to do this, you need to first recognize that the density of water is 1,000 kilograms per meter cubed because it matters what is in this pool. If we filled it with mercury, mercury has a much higher density and it would weigh a lot more than the water would. So we need the density of water, put it to memory, 1,000 kilograms per meter cubed. And we need to know that that density is equal to mass divided by volume. So if we use this formula, we could figure out the mass is equal to the density, rho, times the volume. All right, so we just need to use some of the very little information we have. The 1,000 kilograms per meter cubed, that's going to go in for P, the rho, and we can find the volume of this pool. All right, so we plug in 1,000 for the rho times the volume. Well, the volume of a rectangular prism is length times width times height. So our mass is going to be equal to 1,000 kilograms per meter cubed times 8 meters times 14 meters times 1.5 meters for the length, the width, and the height of this pool. And when you do that, you end up with meters, meters, meters. That would end up being meters cubed. And then we had 1,000 meters cubed here. Those would cancel. Like this meters cubed would cancel with each of these meters. And then we would have a total of 168,000 kilograms. It is a very heavy pool, and water is incredibly heavy, which is why it's very difficult to transfer heat into it. It has a decent amount of energy that it has to be absorbed for it to change in temperature. It also explains why when you're building a deck for a hot tub, you had better make sure it is secured because water is heavy. All right, part B. Calculate the force of the Earth's atmosphere as it exerts on the pool's surface. So we're only concerned about the pool's surface, so we're only concerned about the top of the pool here. So let's go into part B. Part B, atmospheric pressure in general for the Earth at sea level is 1.013 times 10 to the 5th pascals. And pressure is what we're dealing with this time. And pressure is the amount of force divided by the area of the surface that you're caring about. So if we plugged in the pressure of the atmosphere and multiplied by the area, we would end up with our force. Well, the pressure of the atmosphere is 1.013 times 10 to the 5th times the area of this pool. What is the area of the pool? It doesn't care about the depth of the pool. It would only care about the length and the width. So if we multiply that atmospheric pressure times the length and the width, we would end up with the force of Earth's atmosphere that it is exerting on the entire pool's surface. Okay, so it is probably exerting quite a bit. It's exerting a lot, actually. It's exerting 1.1 times 10 to the 7th newtons of force on this entire pool. And you might be like, wow, 10 to the 7th, that's a really big number. And, well, yeah, that is, but it's a very big area. We got 8 meters by 14 meters. That is quite a large surface. And if you think just you belly flopping on the pool surface, your belly would get really red just by that area. Imagine if you belly flopped and you managed to get hit the entire 8 by 14 meter pool, which is, let's see, that's like 24. That's a really big pool. That is 24 across and like 50. That's like a pool you would get at the YMCA or some other big pool, like at the hotel. All right, last one. We got a frisbee. This one's the most important one, I would argue. A frisbee has a radius of 0.1 meters. It's not that big. And it rests at a depth of 1 meter below the pool's surface. Calculate the pressure exerted only on the top of the frisbee. Okay, so only the top of the frisbee because there is pressure exerted on the frisbee below the pool surface. And actually, that's an upward force and the top is a downward force. Okay, we'll get into buoyancy later. So, in order to figure out this one, we have pressure, which is equal to force divided by area. And the force is the weight of the water that is above the frisbee, and the area would just be the area of the frisbee. Okay? So, the pressure exerted on top of the frisbee would be the atmospheric pressure and the weight of the water and all that other stuff because it is open to the air. So we have the weight of the water times gravity, which is equal to rho times height times pi r squared times g. And then we have divided by pi r squared. Now you may be asking, why do we have only pi r squared here instead of the entire area of the pool? Well, the only area that will be affected on this frisbee is going to be the area that is directly the water that is directly above the frisbee. Notice how I got downward areas, all this water that is directly above the frisbee, but only directly above the frisbee. It's not going to be anything outside of that frisbee area that we're concerned about. We're only concerned about the water pressure on the top of the frisbee, which would be the circle of water above it. Okay, so we got rho times height times pi r squared. Those pi r squareds for the area will cancel out. And we have 1,000 kilograms per meter cubed for the density of water times the height that that water is at. Well, the height of that water is 1 meter times gravity, which we're rounding for 10 meters per second squared. And we would end up with 10,000 pascals. Now, this formula right here, rho GH, is a very important formula that I would remember because that stands for the hydrostatic pressure, and it's going to be a part of the next lesson, which will deal with hydrostatic pressure. I'm going to try and keep some of these videos down to just one example because they are they're labor intensive. Okay, so until next time, everybody, stay positive, and I will see y'all later. Bye.